Okay, so what are we looking at here? So what I'm showing you are actually the results of 4 different climate simulations. And for our sake, we're going to say this is over the last 100 years. It's actually the period 1898 to 1999. And what these plots are all showing is for different experiments, the warming trend over that century. So everywhere where you see kind of yellows, oranges, and reds, that means that part of the atmosphere was warming. And everywhere where you see kind of like these blues all the way to these purples, that indicate that the atmosphere was cooling. And the other thing is I'm going to show you the planet Earth, and then really what we're showing is a cross-section of those temperature trends. So kind of this area that's close to kind of the Earth's surface. Remember, this is the troposphere. This is where weather occurs. This is where we live. And then as we get further away from the surface of the Earth, we get into these upper layers. And one of the upper layers we've talked about is the stratosphere. So this panel over here on the right, this is essentially our best hindcast of what the climate system has looked like over the last 100 years. So we're baking our cake, we're throwing in every ingredient that goes into the cake, and we're evaluating how the climate changes. But climate models are pretty cool in that they give us kind of a testbed or an experimental way that we could explore different kinds of Earths to really see what's going on. So we can think about it almost like peeling back the layers of an onion. So let's focus on these first 3 panels here. What I'm going to do is I'm actually going to run 3 different special climate experiments. In this first one, I'm only going to change how our solar input to the system has changed over the last 100 years. I'm going to essentially pretend that the only thing that could be changing temperature in the climate system is just how much sunlight is coming in at the top of the atmosphere. The second panel is going to look at only volcanic eruptions. So again, I'm going to hold everything else the same. The sun is going to stay the same, emissions are going to stay the same. But what just happens when volcanoes emit aerosols, particularly into the stratosphere? And then this third panel is again going to hold the solar radiation fixed. It's going to assume no volcanic eruptions, but it's going to represent the observed increase in greenhouse gases that we've talked about throughout this semester. So let's first come over here and focus on just increasing sunlight. So we've talked a little bit about this, especially in the last couple lessons, but if we increase the amount of sunlight coming into the Earth system, we're increasing the amount of energy into the system, so we should expect to see the temperature warm. And the temperature should actually warm fairly uniformly, whether we're close to the surface or whether we're up here in the stratosphere. And that is generally what we see. We see mostly a lot of yellow. We see kind of a couple of these greeners or these less important warmings. They have to do with kind of some changes in the circulation of the atmosphere. But for the most part, we see what we would expect. When we run the climate model with this particular configuration, we see a lot of yellow and a lot of yellow that's kind of everywhere in the atmosphere. So now we can go over here to the effect of volcanoes. And remember, all we're doing here is we're just simulating volcanoes in the climate system. So what did we learn a few lessons ago? Volcanoes emit a lot of particulate matter into the stratosphere, where it can persist for a fairly long period of time. This particulate matter is mainly composed of 2 constituents, sulfate aerosols. Sulfate aerosols like to reflect incoming solar radiation, which prevents that sunlight from making its way to the surface. So for example, the sunlight would come in, it would find a layer of sulfate aerosols, which are acting like tiny little mirrors, and it will get bounced back out to space. And what that does is it kind of forms like a broad, general, weak cooling in the troposphere. And that's what we see. These colors aren't really high intensity cooling. We're not seeing like a lot of purples, but close to the surface, we're seeing a decent amount of kind of these greenish type colors, which indicate either very little temperature change or a little bit of cooling. We also see a little bit of warming in the stratosphere. And this is because of that black carbon aerosol that goes up. Remember, black carbon aerosols, they're black. Black things like to absorb solar radiation. So as that sunlight comes in, some of it gets reflected by the sulfate aerosols, but some of it gets absorbed by these black aerosols in the stratosphere, which warms the stratosphere. So this is a very common fingerprint that we would expect to see with volcanic eruptions. And then last over here in panel number 3, we see what is the warming trend just from increasing greenhouse gases. And we did talk about this in the past lesson. We said that if the amount of energy into the system is roughly the same, so if the amount of solar radiation is roughly the same, but we're emitting greenhouse gases that are essentially acting like a blanket in the troposphere, what we're doing is we should see a warming signal that's relatively close to the surface in the troposphere, and we should see a cooling signal aloft, because we kind of have a zero-sum game here. So if we have warming in the troposphere, it has to be balanced by cooling in the stratosphere. Again, not increasing the amount of sunlight that's coming in. So we have these 3 different experiments. We can kind of call these things like counterfactuals. That's because they're essentially Earths that kind of we are applying very special conditions to. So remember, this 4th panel over here is kind of our best simulation. This is our hindcast. This is where we take those curves that we were talking about and we make sure that the verification and validation of the models looks really, really good. So of these first 3 panels, which one looks most closely like this 4th panel? Well, I don't really have to take a poll, but hopefully you guys are all pointing to panel number 3. And what is that telling us? That is telling us that in addition to the observational fingerprints that we've talked about earlier, that climate models are providing even further evidence, even more clues, that the warming trends that we've observed over the last 100 years are due to greenhouse gas emissions. That's because our best guess certainly looks a lot like this climate simulation, where all we're doing is increasing greenhouse gas emissions. And this really shows how climate models can be a very powerful tool for scientists to test hypotheses without having to create your own Earth in a different universe or wait hundreds of years to see how the climate is going to evolve.